numerically to find all the roots of the denominator. All saying tiers. I'm saying denominator is singular because they have the same denominator, right? 1 plus product of everything below. The second method is an approximation. Approximate delay so that the closed loop denominators become polynomials. And a specific, particularly valuable method for this approach, great method. Oh, first of all, let me add that this is not safe. If you do that, your approximate system could be closed loop stable, and your real system closed loop unstable coupled. Okay, so it's not safe. But there's a great method here that I will discuss immediately after we finish this outline. It's called the Routh array, and equivalently, I'm not going to discuss it, just historically, those two methods boil down to the same thing, but the Routh array is easier to do so. Routh array. And I will just put the names here. The Bode stability criteria. Which usually applies. And the fourth one that does everything, the Nyquist stability. Always.
That's like Bode stability criterion?
Yeah, I'm not sure how it's pronounced, but I think Bode or Bode, something like that. All right. So, first method is just basically you have the denominator equation and you do the best you can to solve it numerically. So we're going to talk about the second method. And specifically, we're going to talk about the Routh array. The Routh array is not specifically for closed loop stability or anything like that. It's actually something that is very useful for open loop stability also. When am I stable? When all the poles of a transfer function have negative real power. If I have an open loop system, What is the denominator of the transfer function? A polynomial equation. So the poles of an open loop transfer function are the roots of a polynomial. We can check if all have negative real part if we calculate all the roots. We go to Wolfram's side and calculate all the roots. But there's actually a much easier method that you can often do with pen and paper, and it has a huge advantage over going to get the roots from the software. When it comes to closed loop systems. And the advantage is that you don't actually have to solve for the roots. The root array is a method that tells you how many roots of a polynomial have positive real part. Okay? Root array, any polynomial, doesn't matter where we got that polynomial from. It's a method that tells us how many roots of a polynomial have positive real part without having to solve for the roots.
So this is a way to approximate, or this isn't?
No, we haven't yet talked about the approximation. For open loop systems, there's no approximation. For closed loop systems, if we approximate the e to the minus ds, we go to polynomial equation so we can use the root array. Okay? For open loop systems, we can use the root array without any approximation because it's already polynomial. For closed loop systems, it's not polynomial because of the e to the minus ds. We'll talk, after I talk about the root array, we'll talk about approximations for e to the minus ds. Okay? But for open loop systems, no approximation at all. So I could give you an exam problem. I could give you GU equals well, that's going to be a lot of fun. Let's put this forward. Is this open loop stable? No calculators allowed. You say, what's the polynomial? I cannot find the roots. Root array you can immediately do. Okay? So one way you can answer this, if I'm asking you this, is this system open loop stable? Yes, if you have your calculators and they do polynomial solutions, you can find the four roots of the polynomial and see if they all have negative real part or not. If they are all negative, we are stable. If even one is positive, we are not. But with the root array, you can do it pen and paper without doing any kind of numerical solutions. Okay? So let's talk about the root array. Very easy to construct array. The root array method for determining how many roots polynomial has. Sorry for freezing the. With positive, with positive real. Without solving for the roots.
No.
I'll tell you what, this will be a little bit of work. How much work? Let me think. Let's change it to a cubic. Yeah, I don't want to. Let's change it to a cubic so that I spend less time on this example. Okay? So, let me develop the method on this board, and let me do the example on this side. So side by side on your notes, you may want to skip some space for the method and write in 2 places, 1 place for the method and 1 place for the example. So the example is what polynomial I'm interested in finding is that GU stable. Okay? Is this GU stable? So the denominator is S4 plus 3S squared plus 2 equals 0. Example.
You said S4, but it's S cubed.
Oh, sorry, S cubed. Plus 3S squared.
Plus 2.
Yeah, let's see. 4. No, let's make it S4. It's not. I think I need a little more. Let's change it back to S4. 5 rows, what do you think? 5 rows?
Damn it.
So 2 to calculate. Yeah, okay, let's leave it as 4. S4 plus, I'll need some calculator help after the break, or I'll put up Excel. So that's the polynomial we're going to use in the example. So here is it's going to have, it's an array that has n plus 1 rows, where n is order of polynomial. So for our example, so I'll do here the general case. So let me write the polynomial as an s to the n plus an minus 1 s to the n minus 1 plus a1s plus a naught equals 6. Andrea, question? What is that? It's the polynomial that specific example, this let's say the denominator of GU or GDR. So I'm solving the equation, that denominator equals it. Everybody clear? I'm not solving, sorry. I'm looking at the roots of the equation.
What is A, the constant in front of it?
Yeah, just some constant. Like another example, A4 is 1,
Okay.
A3 is 0, A2 is 3, A1 is 0, and A0 equals 2. Okay, this is general equation, this specific example.
Ah.
So, I should have, so I've written that first. So, has n plus 1 rows. So I can immediately form for the root array a structure. Let's see. We'll take the break in 2 minutes. Let me just put the structure and we'll take the break in 2 minutes. So you have a structure in which I'm writing here the rows, row 1, row 2, row 3, row 4, and the last row below n plus 1. In our example, how many rows will I have?
5.
5.
Oh.
Row 1, 2, 3, 4, 5. Okay? Let's take the break now. Really, I think you missed the point that you need a break.